So here's something worth thinking about as you settle in tonight. Right now, in the dark, your ears are doing something extraordinary. Someone whispering in the next room produces sound waves that carry, physically, about 1 trillionth of a watt of energy per square meter. A loud rock concert produces sound waves that carry about 1 watt per square meter. That is a difference of 1 trillion to 1, a ratio of 10 to the 12th power. And yet your auditory system doesn't experience these two sounds as being a trillion times apart. The whisper sounds quiet, the concert sounds loud, and the distance between them, in your subjective experience, feels manageable. A difference you can navigate. Not a trillion, something closer to a dozen steps, each one doubling the perceived volume. Your ear is not measuring sound intensity linearly, it is compressing it. It is, in a precise mathematical sense, taking the logarithm of the incoming signal, scaling an incomprehensible span of 1 trillion to 1 down into something your brain can actually use. The same is true of your eyes. The same is true, to a significant degree, of your sense of touch, your sense of pain, your intuitions about the sizes of numbers and the passage of time. You are, at the level of your basic perceptual architecture, a logarithm computing machine. You have been computing logarithms since the moment you were born. You just didn't have a name for it. And that's what we're going to talk about tonight. Logarithms. The whole confusing, beautiful, quietly profound thing. From the moment a Scottish nobleman invented them to save navigators from drowning in arithmetic, to the way they appear in earthquake scales and pH chemistry and the information theory that underlies every computer, to the way they map onto the deepest structure of how your brain perceives the world. We're going to take it slow, start from the very beginning, and just walk through it together. No rush. If you drift off somewhere along the way, that's perfectly fine. The ideas will still be here. And honestly, some of this makes more sense when you're half asleep anyway. When your mind is loose and not fighting the formulas, just letting the shape of the ideas settle in. And the beautiful thing is, you don't need to be a mathematician to follow this. You really don't, because logarithms at their heart are about something you already understand, the question of how many times you need to multiply. That's it. That is the entire idea. Everything else, the strange notation, the symbol ln, the mysterious number e, the pH scale, the decibel, all of it is downstream of that one simple question: how many times do I need to multiply? The complexity is in the applications, not in the core, and the core, once you see it clearly, is one of the most elegant and useful ideas in all of mathematics. We're going to take our time. We're going to start well before logarithms existed, before anyone had thought of them, when the people who needed them most were suffering without them, because the story of logarithms doesn't begin with a mathematical insight. It begins with a practical crisis. It begins with people drowning in numbers, desperately in need of a shortcut, and one man who spent 20 years of his life building it for them. Let's start where the story actually starts, which is the late 16th century, somewhere around 1590, and the mood among people who did serious calculation for a living was, honestly, one of grinding exhaustion. Think about what it meant to do arithmetic in 1590. There were no calculators, no computers, no mechanical aids of any kind, except possibly an abacus, which helped with addition and subtraction, but not with multiplication and division. If you needed to multiply two large numbers together, say, two 6-digit numbers, you did it entirely in your head and on paper, digit by digit, carrying your remainders, tracking columns, the whole laborious process. And the larger the numbers, the worse it got. Not just twice as hard, or 10 times as hard, much worse than that. The number of individual arithmetic operations required to multiply two n-digit numbers by hand scales roughly with n squared. So multiplying two 6-digit numbers requires something on the order of 36 individual multiplications and additions. Two 8-digit numbers, 64. Two 12-digit numbers, 144. And the more operations, the more chances for error. One miscarried digit, one momentary lapse of attention, and your answer is wrong, and you might not know it. You might carry that wrong number forward through another 20 steps of calculation and only discover the error, if you ever did, by checking your work from scratch. For certain people in the late 16th century, this was not an abstract inconvenience. It was a genuine, career-defining, sometimes life-threatening problem. Astronomers were among the worst afflicted. The great Danish astronomer Tycho Brahe, who lived from 1546 to 1601, and who built, on the island of Haven off the coast of Denmark, the most sophisticated naked-eye observatory in the history of the world, was accumulating observations of planetary positions at an extraordinary rate. Night after night, year after year, Tycho and his assistants measured the positions of planets against the background of stars with a precision that had never been achieved before. He had enormous, beautifully engineered brass instruments, quadrants and sextants and armillary spheres, capable of measuring angles to an accuracy of about 1 arc-minute, which was roughly 20 times better than anything that had come before. He was building up a catalog of planetary positions that would eventually allow his young assistant, Johannes Kepler, to discover the laws of planetary motion. But to use those observations, to compare them with theory, to calculate what the planets should be doing according to any given model of the solar system, to check predictions against measurements, required arithmetic. Enormous quantities of arithmetic. Trigonometric calculations involving sines and cosines and tangents of angles, which themselves had to be looked up in tables and then multiplied and divided with other large numbers. A single check of a planetary position against theory might require hours of calculation. An astronomer doing this kind of work every day would spend more time calculating than observing, and the error rate was significant enough that results had to be verified repeatedly. Let's actually sit with what large number multiplication felt like in that era, not abstractly, specifically. Imagine you are a navigator on a Spanish galleon in 1595, trying to verify your position using a spherical trigonometry formula. The formula requires you to compute the product of two numbers, let's say 7,382,641 and 4,917,053. These are not unusual numbers for this kind of calculation. You have no mechanical aid. You have a pen, ink, and paper. You begin by multiplying 7,382,641 by 3, the last digit of the second number. That gives you 22,147,923. You write it down. Then you multiply 7,382,641 by 5, the next digit, and shift it one place to the left. That gives you 36,913,205, written offset by one position, then by 0 zeros, then by 751,678,487, shifted 3 places, then by 17,382,641, shifted 4 places, then by 966,443,769, shifted 5 places, then by 429, 549 individual multiplications and 7 column additions, with carrying at every stage. One wrong carry, one moment of distraction between multiplying 6 times 7 and remembering to add the carried 3, one smudged digit on damp parchment in rolling seas, and your answer is wrong, and you may not know it. And the wrong answer will feed forward into the next calculation and the next, until eventually the ship arrives somewhere other than where it was supposed to. or doesn't arrive at all. The arithmetic of navigation was, in the 16th century, both the most essential skill in the profession and the most exhausting and error-prone. Navigators weren't bad at arithmetic. They were human beings doing too much of it, under difficult conditions, with everything at stake. Navigators were in an even more precarious position, and for them, the stakes were literally fatal. A ship's navigator in the late 16th century, trying to determine his position in the open ocean, needed to perform celestial navigation, measuring the altitude of the sun or stars at known times, then computing his latitude and longitude from those measurements using spherical trigonometry. Spherical trigonometry is, arithmetically, among the most demanding branches of practical mathematics. It requires multiplying together numbers with 8, 10, 12 significant figures. A navigational error that places a ship 10 miles from where it actually is might seem minor, but 10 miles off course when approaching a rocky coastline in bad weather, or when trying to make a safe harbor after weeks at sea, could mean the loss of the ship and everyone aboard. Errors in calculation killed people. The arithmetic burden of practical navigation was not merely annoying, it was a genuine hazard. And it wasn't just astronomers and navigators, surveyors mapping land, architects computing load-bearing structures, engineers calculating trajectories, merchants doing exchange calculations across multiple currencies. Anyone who worked with numbers seriously in the late 16th century was laboring under the same brutal arithmetic burden. Multiplication was hard, division was harder. Raising a number to a power was nearly impossible, except for small integers. The machinery of practical mathematics was creaking under its own weight. What was needed was a shortcut, something that would take the enormous numbers that practical calculation required and make them manageable, something that would replace the hardest arithmetic operations with simpler ones. And in 1614, that shortcut arrived. It came from a most unlikely source. A Scottish nobleman who had spent 20 years working on mathematics as a private obsession, in relative isolation, motivated partly by the genuine desire to help, and partly, it seems, by the sheer pleasure of the puzzle. His name was John Napier. John Napier of Merchiston was born in 1550 in Edinburgh, Scotland, at a castle called Merchiston Tower, which still stands today as part of what is now Edinburgh Napier University. He was the 8th Laird of Merchiston, a Scottish landowner, a man of property and title, not a professional mathematician. He managed his estate. He was deeply involved in the religious controversies of his time, a committed Protestant in an era of fierce theological conflict, and he wrote a book-length commentary on the Book of Revelation that was, for a time, more famous than any of his mathematical work. He was interested in military engineering. He designed some extraordinary and fanciful weapons, including a burning mirror that would set enemy ships on fire at a distance, and a round metal chariot impervious to bullets. Many of these were never built, but they testify to a restless, inventive, obsessive mind. And somewhere around 1590, Napier turned that obsessive mind toward a problem that had been bothering practical mathematicians for years, the problem of large number multiplication. His approach was, to put it mildly, unusual. He did not start from the idea of logarithms as we now understand them. He started from a completely different place, from a Gedanken experiment involving 2 points moving at different speeds along 2 different lines. Imagine 1 point moving along a finite line segment, always moving at a speed proportional to how much of the line remains. So it starts fast, then slows down as it approaches the end, its speed always equal to the remaining distance, so it never quite reaches the end. It's always moving, always slowing. Alongside it, a second point moves along an infinite line at constant speed. Now, What is the correspondence between the positions of these 2 points? At any given moment, you can pair up the position of the first point on its finite segment with the position of the second point on its infinite line. Napier called the position of the second point, the one on the infinite line, the logarithm of the corresponding position of the first point. The word logarithm comes from 2 Greek roots, logos, meaning ratio, and arithmos, meaning number, the number of the ratio number. This is not how we introduce logarithms today, and it is not the clearest way to understand them. But it was how Napier thought about them, because it allowed him to see the key property that makes logarithms useful, the correspondence between geometric sequences and arithmetic sequences. Here's what that means. Take the sequence 1, 10, 100, 1000, 10,000, 1,000,000. Each number is 10 times the previous one, a geometric sequence, growing by multiplication. Now look at the exponents. 0, 1, 2, 3, 4, 5. Those exponents form an arithmetic sequence, growing by addition. The multiplicative structure of the first sequence corresponds to the additive structure of the second. If you want to multiply 100 by 1000, you can instead add their exponents, 2 and 3, to get 5, and then look up 10 to the 5th power, which is 100,000. Multiplication has become addition. Just sit with that for a second. Multiplication, the slow, error-prone, laborious multiplication that was consuming hours of astronomers' and navigators' lives, has become addition, one of the simplest operations in arithmetic. And if you have a table that tells you the logarithm of any number, not just the round powers of 10, but every number between them, to many decimal places, then you can replace any multiplication problem with an addition problem. Look up the logarithms of the 2 numbers, add them, look up what number corresponds to that sum. You've just multiplied without multiplying. Napier spent roughly 20 years computing his tables. 20 years, working by hand, calculating the correspondence between his sequences of numbers, with the slow patience of someone who understood exactly how much the answer mattered. He introduced his system not in base 10, that refinement came later, but in a form built around a starting value of 10 million, which reflected the precision of the trigonometric tables in use at the time, which themselves tabulated angles to 1/10,000,000th parts. The result was cumbersome in some ways, but it worked. It gave the right answers. And when he published it in 1614, in a book called Mirifici Logarithmorum Canonis Descriptio, a description of the admirable table of logarithms, the reaction from the mathematical community was immediate and extraordinary. Johannes Kepler, who at that time was still laboring over the astronomical calculations that would become his laws of planetary motion, heard about Napier's tables and is reported to have wept with joy. Wept, because he understood instantly what Napier had done. Years of calculation suddenly compressed. The computational burden that had been the constant companion of anyone doing serious astronomy halved, more than halved. The amount of time required to reduce an astronomical observation to a usable number dropped dramatically. Kepler later wrote that Napier had lightened the burden of astronomers. It was one of the most consequential gifts one mathematician had ever given to a scientific community. Now, Napier's logarithms were powerful, but not perfectly elegant. They were built around a strange base, not 10, not 2, not the natural mathematical constant we now call E, but an unusual value related to his kinematic construction. They worked, but they required careful handling, and converting between them and the decimal number system that practical people used required extra steps. A simpler, cleaner version was clearly possible, and the man who saw how to build it traveled to Scotland to meet Napier personally. Henry Briggs was, in 1614, the first professor of geometry at Gresham College in London, a position created specifically to bring mathematical education to the practical men of the city: merchants, navigators, surveyors. Gresham College was not a university in the traditional sense. It was a place where the working professionals of London could come to hear lectures on subjects useful to their trades. Briggs lectured on navigation, on astronomy, on practical mathematics. He was, in other words, precisely the kind of person who understood most acutely why Napier's invention mattered and exactly what its shortcomings were. He read the Descriptio in 1614, recognized at once what it was, and wrote to a friend that he had never seen a book that pleased me better or made me more wonder. Then he did something remarkable. He packed his bags and traveled to Edinburgh to meet the man who had written it. The story of their first meeting, as recorded by the English mathematician William Lilly a few decades later, is one of the most charming in the history of mathematics. Briggs arrived at Napier's house. He was brought into a room where Napier was waiting, and then, according to Lilly, the two men sat and looked at each other in silence for nearly a quarter of an hour, just looking, each in silent admiration of the other, neither able to speak. It was Briggs who finally broke the silence, saying that he had come from a great distance and had wanted only to see with his own eyes the man who had invented this extraordinary thing. Napier, reportedly, said he was delighted to return the compliment, and they got to work. Briggs had a proposal. Instead of Napier's original system, with its awkward base, what if they built logarithms around base 10? The logarithm of 1 would be 0, because 10 to the 0 power is 1. The logarithm of 10 would be 1. The logarithm of 100 would be 2. The logarithm of 1,000 would be 3. And every number in between would have a logarithm between those whole numbers, a decimal value that could be computed and tabulated. This would make the tables much easier to use, because in the decimal number system that everyone already used, multiplying or dividing by 10 just shifted the decimal point, and the logarithm to base 10 captured that naturally. The logarithm of 3,500 would be the logarithm of 3.5 plus 3, because you just shift 3 decimal places. The same table works for any scale. Napier agreed. He died in 1617, before the full base 10 table was complete. But Briggs took up the work and in 1624 published his Arithmetica Logarithmica, the logarithmic arithmetic, containing 14-digit base 10 logarithms for the numbers 1 through 20,000 and 90,000 through 100,000, the gap in the middle left for others to fill. It was a monumental act of computation, essentially the world's most useful mathematical table at the time of its publication, and it remained in use, in updated and extended versions, for 350 years, until electronic computers made manual logarithm tables obsolete in the late 20th century. The actual construction of the tables was a massive undertaking. Napier's approach used what he called the geometric and arithmetic progressions. He needed to build a correspondence between two sequences: a geometric sequence, in which each term is a fixed ratio of the previous, essentially the original numbers you want to work with, and an arithmetic sequence, in which each term is a fixed increment above the previous, the logarithms. To generate enough precision to be useful for astronomical and navigational work, he needed to compute millions of individual values, each requiring multiple multiplications and additions to generate from the previous ones. He did this systematically, in stages. He started with values very close to 1, differing by tiny amounts, and used iterative multiplication to generate thousands of values in the geometric sequence. Think of building a very fine ladder of numbers, each rung very slightly above the last, extending across the full range from 1 to 10 million. Each rung required a multiplication To generate a table with enough precision to be useful, entries for every 100,000th of a unit, required roughly 1,000,000 individual calculations. Working alone, or nearly so, by hand, in a castle in Scotland, before his other duties as an estate manager and theological writer, Napier did this over roughly 20 years. Perhaps not every year, perhaps with long breaks, but 20 years from inception to publication. The sheer patient labor of it is almost incomprehensible. No recognition during those years, no colleagues checking his work, just a man with a quill and an obsession, slowly building a tool that the world did not yet know it needed, but would use for 3.5 centuries. Kepler's response to Napier's tables deserves more than a passing mention, because it illustrates something important about the way mathematical tools change what scientists can do. Johannes Kepler had been working for nearly a decade on what would become his Astronomia Nova, the New Astronomy, published in 1609. In it, he proved that the orbit of Mars was not a circle, but an ellipse, with the Sun at one focus. This was one of the most important results in the history of astronomy. But reaching it required calculating the position of Mars on its orbit at hundreds of specific times, comparing those positions with Tycho's observations, testing hypothetical orbital shapes, rejecting them, trying again. Each such test required working through the arithmetic of trigonometry, sines and cosines of angles, multiplied and divided with orbital parameters, repeated hundreds of times. The calculation burden was immense. When Kepler first encountered Napier's Descriptio in 1616, he was in the middle of the calculation work that would become his third law of planetary motion, the law relating the period of a planet's orbit to the size of its orbit. He immediately grasped what logarithms would allow him to do, and he wrote to a friend, "I truly praise Napier in particular for the benefit he has brought to astronomy, and I thank him with all my heart for his invention." He described the tables as having saved him months of labor. He used them extensively in the remaining years of his career. The impact extended beyond any individual scientist. The astronomical tables that Kepler published in 1627, the Rudolphine tables, based on Tycho's observations and Kepler's orbital mechanics, the most accurate astronomical tables ever produced at that point, were computed using logarithms. They were used by navigators and astronomers for generations. Galileo used similar tools. Newton, who was born in 1643 and who built much of his early work on Kepler's results, had access to Briggsian logarithms that were by then well established. The entire trajectory of 17th century science, the scientific revolution that transformed humanity's understanding of the universe, was facilitated, in a very practical way, by a 20-year computational effort that a Scottish nobleman undertook in a castle in Edinburgh. This is not to overstate the case. The scientific revolution would have happened without logarithms, eventually. The ideas were ready, the observations were accumulating, but logarithms made the calculations faster and more reliable. They allowed the people doing the work to spend more time thinking and less time computing. And in science, as in all creative work, the thinking is the thing. Anything that removes friction from the calculation to free up time for thought is not a minor convenience. It is a force multiplier on human intellectual capacity. These are now called the common logarithms, or Briggsian logarithms, or simply log base 10. When you see log 10 in a textbook, or when someone writes log without a base specified in a context involving powers of 10 or decibels or pH, these are the logarithms Briggs built. And let's be concrete about what it actually felt like to use logarithm tables in practice, because this is something that almost no one alive today has done, and the experience is worth imagining. A printed log table, the kind used by engineers and scientists well into the 20th century, was a book. Not a thin pamphlet, a substantial book, typically with tables covering numbers from 1 to 10, with entries for every 10,000th or 100,000th, and their logarithms given to 4, 5, or 6 decimal places. You would open it to the page for the first 3 digits of your number, find the row for the 4th digit, find the column for the 5th digit, and read off the logarithm. If you needed more precision, there were interpolation tables that let you estimate the logarithm for numbers between the tabulated values. To multiply 2 numbers, you looked up both logarithms, wrote them down, added them on paper, a simple addition of 2 decimals, and then found the number corresponding to that sum in the antilogarithm table. The antilog table runs in the opposite direction. Given a logarithm, find the original number. 3 table lookups and 1 addition. Compared to the column-by-column multiplication of 2 large numbers, this was astonishingly fast. A skilled user of logarithm tables could multiply 2 8-digit numbers in perhaps 30 seconds, compared to several minutes without. For repeated calculations, as in navigating a ship or reducing a night's worth of astronomical observations, the time savings were enormous. And the error rate dropped dramatically. Not because logarithm tables were error-free. Early editions had mistakes, which were found and corrected over subsequent editions, often by the cumulative checking of generations of users, but because each table lookup was a simple read and copy operation, not a complex multi-step mental process. The chances of introducing a new error in any given calculation were much lower. Over the 17th, 18th, and 19th centuries, the logarithm table became as fundamental to quantitative work as the written language was to scholarship. You could not do serious science or engineering without it. Every university had copies. Every ship carried them. Libraries stocked them. Different editions covered different precision levels. The great mathematical tables project of the 19th century, driven partly by the British Association for the Advancement of Science, produced tables of unprecedented precision and reliability, with error-checking processes that involved teams of human computers working in parallel to verify each other's results. Charles Babbage, who would later conceive of the programmable mechanical computer, was motivated partly by the errors he found in these mathematical tables and by his conviction that a machine could produce them more reliably. The logarithm table, in this sense, is one of the intellectual ancestors of the computer. Now, let's stop and actually understand what a logarithm is. Because we've been talking about the history, and the history is wonderful, but it's worth making sure we have a clean picture of the mathematics before we go further. A logarithm answers one question, one simple question. The question is, to what power do I need to raise this base to get this number? That's it. That is the whole definition. Log base 10 of 1,000 asks, to what power do I raise 10 to get 1,000? The answer is 3, because 10 to the third power equals 1,000. Log base 10 of 100,000 asks, to what power do I raise 10 to get 100,000? The answer is 5, because 10 to the fifth power is 100,000. Log base 10 of 10 asks, to what power do I raise 10 to get 10? The answer is 1, because 10 to the first power is 10. Log base 10 of 1 asks, to what power do I raise 10 to get 1? The answer is 0, because anything to the 0 power is 1. And here is where it starts to feel strange and interesting. Log base 10 of something between 1 and 10, say 5, is a number between 0 and 1, because 10 to the 0 power is 1, and 10 to the first power is 10, and 5 is in between them, so its logarithm must be between 0 and 1. Specifically, it's about 0.699, meaning 10 to the power 0.699 is approximately 5. You can verify this on any calculator. And log base 10 of something between 10 and 100, say 50, is a number between 1 and 2. Log 10 of 50 is about 1.699. 10 to the 1.699 is approximately 50. Now here is the key insight, the thing that made logarithms worth 20 years of Napier's life. When you multiply two numbers, their logarithms add. When you divide two numbers, their logarithms subtract. Always, without exception. This is the fundamental property that makes the whole system work. Why is this true? Because of how exponents behave. You already know, or you once knew in some school classroom somewhere, that when you multiply two powers of the same base, you add the exponents. 10 to the third times 10 to the fourth equals 10 to the seventh. 3 plus 4 is 7. That's the rule for exponents. And logarithms are just exponents. They are the exponents you need. So when you multiply two numbers together, you're combining their exponents. And combining exponents means adding them. The logarithm of a product is the sum of the logarithms. Always. Think about what this means in practice. In 1614, to multiply two 8-digit numbers together, a navigator or astronomer would look up each number's logarithm in Napier's table, add the two logarithms, which is just addition, trivially simple, and then look up what number corresponds to that sum. One addition, two table lookups, instead of dozens of individual multiplication steps, and the result is accurate to whatever precision the table provides. The effort saved is staggering. In an era before any mechanical calculation, this was transformative. It changed what was computable, who could compute it, and how long it took. The same principle applies to division. The logarithm of a quotient is the difference of the logarithms. To divide two numbers, subtract their logarithms and look up the result. And for powers, the logarithm of a number raised to an exponent is the exponent times the logarithm of the number. Log of x to the nth power equals n times log of x. So if you want to compute the fifth power of some large number, you look up its logarithm, multiply that logarithm by 5, and look up the result. You've computed a fifth power using only multiplication by 5. And if 5 is itself small enough, that multiplication is trivial. And square roots, cube roots, any root, the logarithm of the square root of x is half the logarithm of x. To find a square root, look up the logarithm, divide by 2, look up the result. Finding square roots, one of the most tedious and error-prone calculations in pre-logarithm arithmetic, becomes a lookup and a halving. These properties are not coincidences or clever tricks. They are direct consequences of what a logarithm is, because a logarithm is an exponent, and exponents have these properties. The logarithm inherits all of them. Here's another way to feel what the logarithm is doing, which sometimes helps alongside the formal definition. Think about how you describe the size of something. When you say a crowd of people is big, you probably mean a few thousand. When you say a city is big, you probably mean a few million. When you say the national debt is big, you probably mean a few trillion. Your implicit sense of what counts as big scales with the context, with the domain of the quantity. And that scaling is, roughly, logarithmic. A city 1,000,000 times bigger than another city doesn't feel 1,000,000 times bigger. It feels maybe 5 or 10 times bigger, because your sense of scale has been adjusting logarithmically as you moved from one to the next. Or think about time. 1,000 years ago feels about twice as remote as 500 years ago. 10,000 years ago feels about twice as remote as 1,000 years ago. 1,000,000 years ago, the deep past of human prehistory, feels about twice as remote as 10,000. And 1,000,000,000 years ago, the age of early life on Earth, feels about twice as remote as 100 million. If you drew a timeline to scale, With 1 millimeter for each year, a billion years would stretch for 1,000 kilometers. But in your sense of historical depth, all of those eras feel roughly comparable in remoteness, because your sense of historical time is logarithmic. You are not naturally equipped to feel the linear difference between 1,000 years and a billion years. You are equipped to feel the logarithmic difference, the difference in order of magnitude, and that is enough to navigate. The logarithm is the mathematics of that sense. It converts the linear scale of absolute quantities into a scale of orders of magnitude, and orders of magnitude are, very often, exactly what you care about. Now, as we've been discussing, this works cleanly when the numbers involved are nice powers of 10, but the power of logarithm tables comes from the fact that they cover every number between the powers, every decimal value between 1 and 10, mapped to its logarithm to many significant figures. Napier's original table had more than 10,000 entries. Briggs's table had tens of thousands. They covered the space between the whole number powers with a fine enough grid that any practical calculation could be done to the required precision. This is what took the labor, computing those intermediate values by hand, digit by digit, over years. If you've ever used one of those printed log tables in the back of a math textbook, the ones with columns of 4-digit or 5-digit numbers, you've seen the legacy of Napier and Briggs. If you've ever used a slide rule, you've used their ideas in physical form. And if you've ever calculated a pH or a decibel level, or checked an earthquake magnitude, you've used their system, probably without knowing who built it or what they sacrificed to do so. Now, there's something else, something that sits alongside base 10 in the world of logarithms, and that in many ways is more fundamental, more natural. It appears in growth and decay. It appears in probability and information. It appears in physics and chemistry and finance. It is, in a precise sense, the one logarithm that the universe itself seems to prefer. It is called the natural logarithm, and it is built around a number that is one of the strangest and most wonderful constants in all of mathematics, the number e. E is approximately 2.71828828459045235536. The digits go on forever, in no repeating pattern, just like pi. It is irrational, like pi. It is transcendental, like pi, meaning it cannot be the solution to any polynomial equation with integer coefficients, no matter how complicated. And it shows up in an enormous range of mathematical contexts, often where you least expect it, in a way that has surprised and delighted mathematicians for centuries. The first clear encounter with E in the historical record comes not from a geometer or an astronomer, but from a very practical question about money. In the 17th century, mathematicians and merchants were thinking carefully about compound interest, about what happens when you invest money at interest not just once a year, but multiple times. If you invest a sum of money at an annual interest rate of 100%, doubling it in a year, you end up with twice what you started with. That's compounding once a year. But what if the bank compounds the interest twice a year, at half the rate per period? Then after 6 months you have 1.5 times your original sum, and after another 6 months you have 1.5 times that. 1.5 squared is 2.25. You end up with more. What if you compound 4 times a year, or 12 times, or 365 times, once per day? And what if you compound continuously, meaning infinitely many times per year, with each compounding period infinitely small? Jacob Bernoulli, the Swiss mathematician, was exploring this question around 1683. He was working out what happens to the expression 1 plus 1 over n raised to the nth power as n gets very large, as n goes to infinity. and he noticed that this expression seemed to approach a specific limit, a specific number, somewhere around 2.718, not 2, not 3, something in between, and not an obviously clean fraction or a simple root of anything, just a specific irrational number that the continuous compounding process converges to. He didn't give this number a name. He noted the phenomenon and moved on. It was the Swiss mathematician Leonhard Euler, one of the most prolific and brilliant mathematicians who ever lived, who later studied this constant carefully and chose to denote it with the letter E. Whether E stands for Euler or for exponential depends on who you ask. Euler himself used the letter in 1736, and the convention stuck. The natural logarithm, written ln, for Logarithmus naturalis, is the logarithm to base e. ln of x answers the question, to what power must I raise e to get x? ln of e is 1. ln of e squared is 2. ln of 1 is 0, as always. And for the numbers between, for any positive number, ln gives the continuously compounded growth time it would take to reach that amount, starting from 1 at a growth rate of 100%. This is why it's natural. In continuous processes, in anything that grows or decays at a rate proportional to its current size, the natural logarithm appears inevitably. The populations of cells dividing, radioactive atoms decaying, the charge draining from a capacitor, the temperature of a hot object cooling toward room temperature. All of these follow exponential curves, and the natural logarithm is the inverse of the exponential. It is the function that undoes e to the x, just as the square root undoes the square. The natural logarithm is, in a very deep sense, the language that exponential processes speak. Euler did something else with e that deserves its own pause, because it is one of the most beautiful results in all of mathematics, discovered somewhere around 1740. He found a relationship between e, the imaginary unit I, the square root of -1, and the trigonometric functions sine and cosine. The relationship is e to the power of I times theta equals cosine of theta plus I times sine of theta. This is Euler's formula. And when you plug in theta equal to pi, you get e to the power I times pi equals -1, which means e to the I pi plus 1 equals 0, Euler's identity. 5 of the most important constants in all of mathematics, e, I, pi, 1, and 0, connected in a single equation, each appearing exactly once. Mathematicians have called it the most beautiful equation in mathematics, and it is genuinely difficult to disagree. It is the kind of equation that makes you feel, viscerally, that the universe has a deep mathematical structure, that these numbers are not independent coincidences, but facets of the same underlying reality. It has been voted, in surveys of mathematicians, the most beautiful result in the field, repeatedly, for decades. If you've drifted somewhere along the way, that's fine. Let the ideas drift too. No need to hold all of this at once. Just let it settle. Euler's discovery of e and the natural logarithm opened a door into what mathematicians and physicists came to call the calculus of growth. It turns out that the natural logarithm is not just convenient for describing compound interest. It is the inverse of the unique function that is its own derivative, the function f dash equals e to the x, which has the remarkable property that its rate of change at any point is equal to its own value. The slope at x equals 2 is e to the 2. The slope at x equals 5 is e to the 5. The function is growing at exactly the same rate as its current size. Always, forever. No other function has this property. Think about what this means for anything that grows at a rate proportional to its current size. A bacterial colony, in which each bacterium divides at a constant rate. A savings account accruing interest proportional to its balance. A radioactive substance decaying at a rate proportional to how much of it remains. It's the same mathematics going in reverse. A disease spreading through a population at the start of an epidemic, when each infected person infects a fixed average number of others. All of these processes are described by the exponential function, and the inverse of the exponential function, the function that undoes it, is the natural logarithm. This connection is why the natural logarithm appears so insistently in physics and chemistry and biology. It is the language of proportional growth and decay. Whenever a system's rate of change is proportional to its current state, which is probably the most common dynamical behavior in nature, the solution involves e, and the natural logarithm is the inverse operation you reach for when you want to solve for time. Newton's law of cooling. The temperature of a hot object drops at a rate proportional to how much hotter it is than its surroundings. Exponential decay toward the ambient temperature. Solve for how long it takes to cool from 100 degrees to 50 degrees. Logarithm. The growth of a tumor early in its development, before space and resources limit it, is roughly exponential. The doubling time is related to the growth rate by the natural logarithm of 2. The relationship between the concentration of a drug in your bloodstream and time after dosing. For many drugs, exponential decay, with a half-life determined by the drug's clearance rate. To find out when the concentration has dropped to a safe level for a second dose, logarithm. The Gaussian distribution, the famous bell curve that describes the distribution of so many natural phenomena, from heights to measurement errors to IQ scores, has the natural logarithm woven into its formula. The exponent in the formula for the Gaussian is a quadratic function of the distance from the mean, and e is raised to that exponent. The natural logarithm is there, quietly, at the heart of the most common distribution in statistics. Euler's identity, e to the I pi plus 1 equals 0, connects all of this to the geometry of circles and complex numbers. The imaginary exponential traces a path around the unit circle in the complex plane, and the natural logarithm of a complex number includes information about both its magnitude and its angle. The full reach of the natural logarithm extends into the geometry of space itself, into wave equations, into quantum mechanics, into the description of oscillating systems. There is perhaps no single constant more deeply woven into the mathematics that describes the physical world than e, and there is no function more intimately connected to e than the natural logarithm. Now, after Napier and Briggs, after the publication of the tables, the next major development in the story of logarithms was not a new mathematical theorem. It was a physical object, an object that compressed the power of logarithm tables into something you could hold in your hands, something you could carry in your pocket, something that required no table lookups and no pencil, just a physical understanding of the additive nature of logarithms, built into the geometry of a measuring device. This was the slide rule. William Oughtred was an English clergyman and mathematician who lived from 1574 to 1660. He spent most of his adult life as a vicar in the village of Albury in Surrey, living quietly, tutoring private mathematical students in his spare time, and doing mathematics as an obsession. He was, by several accounts, so absorbed in mathematical work that he forgot to eat, sometimes spending an entire day in calculation without noticing hunger. He wore the same clothes day after day. He was not, in the conventional sense, a practical man, but he built one of the most practical tools in the history of technology. In the years after Napier's tables were published, the mathematician Edmund Gunter had created a logarithmic scale, a physical ruler in which distances were proportional not to the numbers they represented, but to the logarithms of those numbers. On a logarithmic scale, the number 1 is at the far left, and numbers increase to the right, but the distances between them are compressed. The distance from 1 to 10 is the same as the distance from 10 to 100, which is the same as the distance from 100 to 1,000, because each of these intervals represents an equal step of 1 on the logarithmic scale. Gunter used a pair of compasses to add lengths along his scale, performing logarithmic addition, and therefore multiplication, without arithmetic. Open the compasses to the logarithm of 3. Extend them further by the logarithm of 7. The total span corresponds to the logarithm of 21. You've multiplied 3 by 7 using nothing but a physical measurement. Oughtred's insight was to put two of these logarithmic scales next to each other, movably. Instead of using compasses to transfer distances, you just slide one scale relative to the other. Line up the one on the sliding scale with the first number on the fixed scale. Then read off the second number on the fixed scale against the position of the first number on the sliding scale. The answer appears before your eyes. This is the slide rule. Two logarithmic scales, one sliding against the other, performing multiplication and division by physical addition and subtraction of lengths. Oughtred described the basic idea around 1622, and over the next few decades, instrument makers refined and extended it into an increasingly powerful tool, adding scales for squares and square roots, for cubes and cube roots, for trigonometric functions, for logarithms of logarithms. The slide rule became the computing device of the scientific and engineering world, not a niche tool, not a curiosity, the fundamental instrument of quantitative work for professionals across 3 centuries. Engineers designed bridges with slide rules. Physicists worked out nuclear reactions on slide rules. Astronomers calculated orbital parameters with slide rules. The architects of the Hoover Dam used slide rules. The engineers of the Apollo program used slide rules. Neil Armstrong, on his way to the moon, carried a slide rule in the pocket of his spacesuit. Think about that. A direct line from a Scottish nobleman working alone in Edinburgh in 1590, through a pair of tables and a physical measuring device, to the pocket of an astronaut on his way to the moon. The slide rule was killed, almost overnight, by the pocket electronic calculator. In 1972, Hewlett-Packard introduced the HP-35, the first scientific pocket calculator, a device that could compute logarithms, trigonometric functions, and exponentials at the touch of a button to 10 significant figures for $400. By 1975, slide rule manufacturers were going out of business. By 1980, the slide rule was essentially gone from engineering schools. Generations of engineers who had grown up with the slide rule were replaced by generations who had never needed one. But the slide rule changed how people thought about numbers. It made the logarithmic relationship between multiplication and addition not just a mathematical fact, but a physical intuition. Anyone who worked with a slide rule for years developed a feel for logarithmic scales, an understanding, in their hands, of the way numbers compress at the large end and spread out at the small end, of the way multiplication is equivalent to length addition when the lengths are logarithmic. It was, in some ways, an excellent way to develop number sense. And in certain domains, logarithmic scales remain universal, not as computation tools, but as communication tools, as the right way to display certain kinds of information. We use them constantly, even now. Let's talk about one of the most important of those domains, the measurement of sound. When engineers and physicists needed to measure and compare sound intensities in the early 20th century, they faced a version of the same problem that Napier's contemporaries had faced with large number multiplication. The numbers spanned too wide a range to be useful on a linear scale. The softest sound a human ear can detect, the threshold of hearing, corresponds to a physical intensity of about 10 to the minus 12 watts per square meter. The loudest sound a human ear can withstand without immediate damage, something like a gunshot or a jet engine at close range, corresponds to an intensity of about 10 watts per square meter. That's a range of 10 to the 13th power, 13 orders of magnitude, a trillion times. If you tried to draw a graph of these sound intensities on a linear scale, a scale where equal distances represent equal increases, the whisper level sounds would all be compressed into a sliver at one end, and the loud sounds would stretch to the far end, and the graph would be useless. Nothing in the middle would be distinguishable. The scale simply doesn't fit human communication. So engineers adopted a logarithmic scale. They defined a unit called the bell, named for Alexander Graham Bell, as the logarithm base 10 of the ratio of an intensity to a reference intensity, which they took to be the threshold of hearing. In practice, the bell turned out to be too large a unit for everyday use, so they divided it into 10 parts. The decibel, dB. 0 decibels is the threshold of hearing. 10 decibels is 10 times as intense. 20 decibels is 100 times as intense. 30 decibels is 1,000 times as intense, and so on. A quiet library is about 30 to 40 decibels. Normal conversation is about 60 decibels, 1,000,000 times the threshold of hearing. A loud rock concert is about 110 decibels. A jet engine at close range is about 140 decibels. The span from 30 decibels to 140 is enormous in physical terms, a ratio of 10 to the 11th power, 100 billion to 1. But on the decibel scale, it fits comfortably between 30 and 140. The logarithm has made the incomprehensible range into something you can discuss, graph, regulate, and reason about. And here is something beautiful. The decibel scale is not just a convenient mathematical convention. It is, to a significant approximation, how your ears actually work. The logarithmic compression built into the decibel scale mirrors the logarithmic compression built into your auditory system. This is not a coincidence. Engineers chose the decibel scale partly because it aligned with human perception. A sound that measures 10 decibels louder than another sounds roughly twice as loud to a human listener. A sound that measures 30 decibels louder sounds about 8 times as loud. These relationships, which correspond to logarithmic compression, match what human listeners report when they describe volume differences. The decibel scale feels natural to us because our ears are logarithmic instruments. The formal study of the relationship between physical stimulus and perceived sensation dates to the 19th century and to the work of two German scientists, Ernst Heinrich Weber and Gustav Theodor Fechner. Weber was a physiologist who conducted careful experiments on the sensitivity of human perception, studying how much you have to increase a stimulus for a person to notice the change. He discovered something systematic and surprising. The minimum noticeable change in a stimulus is proportional to the intensity of the stimulus. If you're lifting weights, and you can just barely tell the difference when someone adds 10 grams to a 100-gram weight, you'll need them to add 100 grams to notice the difference with a 1 kilogram weight. The threshold for noticing a change is not fixed. It scales with the size of what you're already experiencing. Gustav Fechner, a physicist and philosopher, took Weber's observation and turned it into a mathematical law. If the minimum noticeable difference is proportional to the stimulus, as Weber found, and you add up all those just noticeable differences from some baseline to some current level, what you get is a logarithm. The perceived intensity of a sensation is proportional to the logarithm of the physical stimulus. Loud sounds feel a certain loudness not because of their absolute physical intensity, but because of the ratio of that intensity to what came before. Bright lights feel a certain brightness not because of the number of photons, but because of the ratio. Your sensory systems are fundamentally ratio-detecting systems, and detecting ratios is what logarithms do. This is Weber's law, formalized as the Fechner law, and it applies with reasonable accuracy across a striking range of sensory modalities: sound, light, pressure on the skin, the perceived heaviness of weights, the perceived brightness of colors, the perceived duration of time intervals. Not perfectly, not in all circumstances, not for all people or all stimuli, but as a broad rule of thumb, your perceptions are logarithmic functions of physical reality. You have been computing logarithms since the moment you were born. Weber published his findings on sensory thresholds in 1834 in a book called De Tactu, On Touch. His initial interest was tactile. How sensitive is the skin? How small a difference in the weight of two objects can a person reliably detect? He found that the answer wasn't a fixed absolute weight difference. It was a fixed ratio. The just noticeable difference was always about 1 part in 30 of the total weight. The threshold was proportional to the baseline. He then extended this to other senses. For visual brightness, the just noticeable difference was a fraction of the total brightness. For the length of two lines, the just noticeable difference was a fraction of the total length. The relationship held across modalities, suggesting something general and deep about sensory architecture. Weber called it the principle of proportionality, and it was later named Weber's law in his honor. Fechner, who came to the problem from philosophy and physics rather than physiology, saw the mathematical implication that Weber had not quite articulated. If the minimum noticeable change at any level is proportional to that level, if delta S equals K times S, where S is the stimulus and K is a constant, then what is the total perceived magnitude when the stimulus has grown from some baseline to its current level? You sum up all the tiny just noticeable differences. An integral of delta S over S from the baseline to the current level. And the integral of 1 over S is the logarithm of S. So perceived sensation equals a constant times the logarithm of the stimulus intensity plus a constant. Fechner published this as a law in 1860 in his Elements of Psychophysics, and the resulting formula, S equals K times log doc I0, where I is stimulus intensity and I0 is a threshold intensity, became the first mathematical law of psychology. Not physics, not chemistry, psychology. The first claim that the inner life of a mind could be quantified using the same mathematical tools as the physical world. The law is not perfect. It breaks down at extremes. Very faint sounds and very loud ones don't both follow the same logarithmic curve precisely. Later psychologists, particularly S.S. Stevens in the mid-20th century, proposed power law relationships as better fits for some modalities. But the core insight, that perception compresses physical intensity logarithmically, has proved robust across a remarkable range of senses and circumstances, and it provides a direct bridge between the physical measurement of a stimulus and the psychological experience of it. The decibel scale for sound is not just a convenient engineering unit, it is approximately aligned with how you actually hear. When a sound engineer says that one mix is 6 decibels louder than another, they are saying something about what you will experience, not just about the voltage on the microphone. Music is a perfect illustration of this. The musical scale, in every culture that has developed an elaborate musical tradition, divides pitch into intervals defined by ratios, not differences. The octave is a doubling of frequency. If middle A is 440 Hz, the A an octave above is 880 Hz. Not 440 plus some fixed amount, 440 times 2. The perfect fifth is a ratio of 3 to 2. The major third is a ratio of approximately 5 to 4. Every interval in the Western musical scale, and in the scales of other musical traditions, is defined by a ratio. The distance from C to G is a ratio. The distance from G to D is the same ratio. Because your ear hears pitch on a logarithmic scale, equal multiplicative steps sound like equal pitch steps. This is why, when you look at a piano keyboard, the octaves are equally spaced, but the frequencies they correspond to are doubling. The leftmost octave spans from about 30 Hz to about 60 Hz, a span of 30 Hz. The next octave spans from 60 to 120, a span of 60 Hz. The next spans from 120 to 240, a span of 120 Hz. Each octave covers twice the frequency range of the one before. But because your ear is logarithmic, they all sound the same size. The piano keyboard is a physical realization of a logarithmic scale for pitch. Every time you hear music, you are experiencing the logarithm. The logarithmic scale for stellar brightness is one of the oldest examples of a logarithmic measurement scale in science. Older than Fechner's law, older than the decibel, older even than the formalization of logarithms themselves, the ancient Greek astronomer Hipparchus, working in the 2nd century BCE, divided stars visible to the naked eye into 6 classes of brightness, from first magnitude, the brightest, to 6th magnitude, the faintest visible without a telescope. This classification was entirely intuitive, based on what looked brighter to the human eye. But because the human eye is logarithmic, Hipparchus's equal-seeming steps happen to correspond, quite closely, to equal multiplicative ratios of actual light intensity. When the English astronomer Norman Pogson analyzed the magnitude scale in 1856 with proper photometric equipment, he found that a first magnitude star is roughly 100 times brighter than a 6th magnitude star. And, since there are 5 magnitude steps between first and 6th, each step corresponds to a brightness ratio of about the 5th root of 100, which is approximately 2.512. Each magnitude step is a factor of 2.512 in brightness. 5 steps is a factor of 100. This is the Pogson scale, still used today. So the magnitude scale for stars is a logarithmic scale in which each unit represents a factor of about 2.512 in intensity. Specifically, it is the logarithm base 2.512 of the brightness ratio. It runs, confusingly, in the wrong direction. Lower numbers mean brighter objects. The star Vega has a magnitude of about 0. The full moon has a magnitude of about -13. The sun has a magnitude of about -27. The faintest objects detectable by the James Webb Space Telescope have magnitudes of about +31. The span from the sun to the faintest Webb objects, from magnitude -27 to +31, is 58 magnitude units, corresponding to a brightness ratio of 2.512 to the 58th power, which is approximately 10 to the 23rd, a factor of 100 million trillion in brightness, compressed into a scale that runs from -27 to +31. This is the logarithm doing its work, making a range of 100 million trillion feel like a range of 58. Every time you hear about a star's magnitude, you are hearing logarithms. Every time you read about a faint galaxy detected at magnitude 20-something, or a bright planet at magnitude -something, you are navigating a logarithmic scale that traces its ancestry all the way back to a Greek astronomer 2,000 years ago who divided stars into 6 classes based on nothing more than how they looked to his eyes, and whose intuitions happen to be logarithmic because human perception is logarithmic. He was computing logarithms without knowing it, and the scale he built turned out to have a precise mathematical structure that wasn't recognized for 2,000 years. And let's stay with music for a moment longer, because the logarithmic structure of musical perception goes deeper than just the octave. The equal temperament tuning system, the system used by virtually all modern Western instruments, from the piano to the guitar to the orchestra, divides the octave into 12 equal steps, each called a semitone or half step. What makes them equal? They are equal in the logarithmic sense. Each semitone represents the same multiplicative ratio of frequencies. That ratio is the 12th root of 2, approximately 1.0595. 12 semitones, each a factor of 1.0595, compound to give a factor of exactly 2, 1 octave. The genius of equal temperament, which was worked out in the 16th and 17th centuries and became standard practice by the 19th, is that it allows an instrument to be played equally well in any key. On an instrument tuned in earlier systems, just intonation or mentone temperament, which tuned intervals to exact mathematical ratios, certain keys sounded pure and beautiful, while others sounded horribly out of tune. The compromises required to make all keys equally usable led, over centuries of musical experimentation, to equal temperament, a system in which every interval is slightly impure, but all intervals are equally impure, and no key sounds worse than any other. Equal temperament is, fundamentally, a logarithmic scale. The frequency of each semitone is the previous frequency multiplied by the 12th root of 2. The note names C, C sharp, D, D sharp, and so on up to B are equally spaced on a logarithmic frequency scale. When a musician says they've moved up a half step, they mean they've moved 1 unit on a logarithmic frequency scale. When they say they've moved up an octave, they mean they've doubled the frequency, moved 12 units on the same scale. The entire language of musical interval is a language of logarithms. Johann Sebastian Bach, who lived from 1685 to 1750, was one of the most influential advocates of the well-tempered system that preceded equal temperament. His collection of preludes and fugues, known as the Well-Tempered Clavier, 2 books of 24 preludes and fugues each, covering all 12 major and 12 minor keys, was a demonstration piece, evidence that all keys were usable and beautiful under a suitably tempered tuning. Whether or not Bach himself explicitly understood the mathematics of equal temperament, he was working with its consequences. He was, in effect, exploring a logarithmic space, a musical universe in which equal multiplicative steps through frequency space produced equal-seeming melodic steps to the ear. The well-tempered clavier is, among many other things, a meditation on the logarithm. Logarithms appear in chemistry in a way that affects everyone, whether they've ever taken a chemistry class or not. The pH scale, the familiar scale that tells you whether something is acidic or basic, that runs from 0 for battery acid to 14 for drain cleaner, with 7 in the neutral middle, is a logarithmic scale. Specifically, pH is the negative of the logarithm base 10 of the hydrogen ion concentration in a solution. This needs a little unpacking, because it's one of those cases where the formula is easy to write and harder to truly absorb. Søren Sørensen was a Danish chemist working at the Carlsberg Laboratories in Copenhagen in 1909, the same institution, the brewery, that also made a significant contribution to beer. He was studying the effect of hydrogen ion concentration on enzyme reactions, and he needed a way to describe acidity on a scale that could be easily communicated and compared. The hydrogen ion concentration in aqueous solutions ranges from about 1 molar in very strong acids to about 10 to the minus 14 molar in very strong bases, 14 orders of magnitude. A 14 order of magnitude range of concentration in a domain where every chemist needs to specify and communicate precise values. Sorensen introduced the pH notation as a way to compress this range. pH equals the negative logarithm base 10 of the hydrogen ion concentration. A concentration of 1 molar gives pH 0. A concentration of 10 to the minus 7 molar gives pH 7. A concentration of 10 to the minus 14 molar gives pH 14. The negative sign is there because concentrations in the acidic range are small numbers, and taking the negative of their logarithm gives a positive pH value, which is easier to work with. It's a convention, not a mathematical necessity, but it's a sensible one. What this means in practice is that each unit change in pH corresponds to a tenfold change in hydrogen ion concentration. The difference between pH 6 and pH 7, the difference between slightly acidic and neutral, is not just one unit. It is a tenfold difference in acidity. The difference between pH 5 and pH 7, the range that might separate a strongly acidic rain from neutral water, is a hundredfold difference in acidity. The difference between pH 2, which is about the acidity of lemon juice or stomach acid, and pH 7, neutral water, is a 100,000-fold difference in acidity. Our language tends to smooth over this. We say something is 10 times more acidic without quite feeling what a tenfold difference in ion concentration means for chemistry, for the rate of reactions, for the integrity of biological molecules, for the ability of enzymes to function. The logarithmic compression of the pH scale is both a convenience and, potentially, a source of misunderstanding. When an ecologist says that a lake's pH has dropped from 7 to 5 due to acid rain, they are describing not a 28% decrease in some abstract acidity number, but a hundredfold increase in hydrogen ion concentration. The logarithm makes it look small. The underlying chemistry is not small. The same logarithmic principle governs the Richter scale for earthquake magnitudes, developed by Charles Richter of the California Institute of Technology in 1935. Each 1-unit increase on the Richter scale corresponds to a tenfold increase in the amplitude of the ground motion measured by a seismograph, and roughly a 32-fold increase in the energy released by the earthquake. The difference between a magnitude 5 and a magnitude 6 earthquake is not 20% more energy, it is 32 times more energy. A magnitude 7 releases about 1,000 times the energy of a magnitude 5. A magnitude 9, like the 2011 Tohoku earthquake that triggered the Fukushima disaster, releases about 1,000,000 times the energy of a magnitude 5. The logarithm makes the scale legible, but it can lull you into underestimating the differences it represents. This is one of the genuine dangers of logarithmic scales in public communication. They compress vast differences into small-looking numbers, and people who don't know they're looking at a logarithmic scale will systematically underestimate how different the extremes are. An earthquake that is 2 points higher on the Richter scale is not twice as bad. It is 1,000 times worse in energy terms. Understanding logarithms is not just a mathematical nicety. It is a matter of accurately perceiving the world. Logarithms also sit at the heart of computer science, in a way that shapes everything from how quickly your phone searches your contacts to how securely your financial information is encrypted on the internet. When computer scientists want to describe how the running time of an algorithm scales with the size of the problem it's solving, they use a notation called Big O notation, an algorithm that takes O-NOS time, order n, takes time proportional to the size of the input. If you double the input size, it takes roughly twice as long. An algorithm that takes O non-squared time takes time proportional to the square of the input size. Double the input, and it takes 4 times as long. And an algorithm that takes O.log n time, order log n, is the best kind. The time grows only logarithmically with the input size. Double the input, and the algorithm takes only a tiny bit longer. Multiply the input by 1,000,000, and the algorithm takes only about 20 times longer, because the logarithm base 2 of 1,000,000 is about 20. Binary search is the simplest and most beautiful example of an O log n algorithm. Suppose you have a sorted list of 1,000,000,000 items, 1,000,000,000 phone numbers in alphabetical order, say, and you want to find out whether a particular number is in the list. The naive approach is to check every number from the beginning. In the worst case, you check all 1,000,000,000. But with binary search, you start in the middle. Is the number you're looking for greater than or less than the middle item? If it's less, the number must be in the first half. Discard the second half. Now check the middle of the remaining half. Greater or less? Discard half again. Each step cuts the remaining possibilities in half. After 30 steps, a list of 1,000,000,000 has been reduced to one item. 30 steps to search 1,000,000,000 items, not 1,000,000,000 steps. 30. Why 30? Because the base 2 logarithm of 1,000,000,000 is about 30. Each halving step moves 1 unit on the logarithmic scale. Binary search converts a multiplicative reduction in the search space into an additive step count. It is, in a very precise sense, a logarithm computed physically. The number of halvings needed is the logarithm base 2 of the original list size. This logarithmic efficiency is what makes so many things in computing fast. Database indexes, which allow databases containing billions of records to answer queries in milliseconds, sorting algorithms that organize data in O(n) log n time rather than the O(n) squared of naive approaches, the binary representation of numbers itself, in which the number of digits needed to represent a number grows only logarithmically with the size of the number. And then there is cryptography. The security of most modern encryption, including the encryption that protects your banking information, your email, your private messages, rests on the difficulty of the discrete logarithm problem. Here is the idea. In ordinary arithmetic, if someone tells you that 10 to the power of x equals a certain large number, you can find x by computing the logarithm. That's easy. But in modular arithmetic, arithmetic done on a clock face, where numbers wrap around after reaching some maximum, the same problem becomes extraordinarily hard. If someone tells you that a certain base raised to a certain power, modulo a large prime, equals a certain number, finding the original exponent, the discrete logarithm, appears to be computationally intractable for large enough numbers, even for the most powerful computers currently available. This hardness is the foundation of the Diffie-Hellman key exchange, the RSA algorithm, and elliptic curve cryptography. Every time you connect to a website via HTTPS, the padlock in your browser's address bar, your computer and the server are using the hardness of the discrete logarithm problem to establish a shared secret that an eavesdropper cannot efficiently compute. The security of the modern Internet rests on the logarithm being hard to invert in certain mathematical settings. Now, among the most important and least understood applications of logarithms in the modern world is their role in information theory, a field that, more than any other, determines the shape of the technological world we live in. Every phone call, every email, every photograph, every video, every piece of data that moves through any wire or through the air in any wireless signal, all of it is quantified, compressed, transmitted, and decoded using ideas that are fundamentally logarithmic. And the person who built that framework, almost entirely alone, in a short burst of work in the late 1940s, is one of the most important and least famous scientists of the 20th century. Claude Shannon was born in 1916 in Petoskey, Michigan. He grew up in Gaylord, a small town in the northern Lower Peninsula, where his father was a judge and his mother the principal of the local high school. He was curious and mechanically gifted from childhood. He built radios from scratch as a teenager, strung a telegraph wire to a friend's house a half-mile away, rigged mechanical contraptions of various kinds. He went to the University of Michigan, where he studied mathematics and electrical engineering simultaneously, then to MIT for graduate school, then to Bell Telephone Laboratories, where he would spend most of his career working on the theoretical foundations of communication. In 1948, Shannon published a paper called A Mathematical Theory of Communication in the Bell System Technical Journal. It was 55 pages long. It changed the world. The central question Shannon was asking was this: how do you measure information? Not in any subjective sense, not how much does this information matter to me, or how much effort did it take to acquire, but in a precise, objective, mathematical sense. How much information is contained in a given message, and what is the maximum rate at which information can be reliably transmitted through a channel that is subject to noise? Shannon's answer to the first question was elegant and, in retrospect, almost inevitable. The information content of a message, he argued, should be inversely related to the probability of that message. A message that says something you already knew with certainty, the sun rose this morning, contains no information because its probability is 1. A message that says something completely unexpected, the sun rose in the west this morning, contains enormous information because its probability is nearly 0. The information content of a message is the logarithm base 2 of 1 over the probability of that message. Equivalently, it's the negative of the logarithm base 2 of the probability. And the unit of this information is the bit. Why base 2? Because bits are the natural unit of information in a binary world. A message that is one of two equally likely possibilities, a coin flip, a yes or no answer, contains exactly 1 bit of information. A message that is one of 4 equally likely possibilities, like which of the 4 suits a randomly drawn card belongs to, contains 2 bits, because you need 2 binary yes-no questions to pin it down. A message that is one of a million equally likely possibilities contains about 20 bits, because 2 to the 20th power is about a million. And why does this have anything to do with logarithms? Because the binary logarithm, the logarithm base 2, is what converts a probability into a bit count. The bit count of a message is log 2 of 1 over the probability. That's it. The information content of an event is the logarithm base 2 of its surprise. The average information content of a source, averaged over all possible messages it might send, weighted by their probabilities, is what Shannon called entropy. And the formula for entropy is the sum over all possible messages of the probability of each message times the logarithm of 1 over that probability. It looks like h equals minus sigma p di I log 2 p di i's. This is Shannon entropy, and it measures how uncertain you are about what a source will say next, how much information you'd gain, on average, from learning it. Shannon entropy is one of the most important quantities in modern science and engineering. It tells you the theoretical minimum number of bits needed to represent a message. It tells you how much you can compress data. It tells you how much redundancy you need to add to a message to make it robust against noise. Every compression algorithm, the ones that make your images smaller, your music files more compact, your videos streamable, is working within limits set by Shannon's entropy formula. Every error-correcting code, the ones that allow data to be recovered even when bits are flipped by noise, is built on the framework Shannon created. The Internet, in a very specific and quantifiable sense, runs on the logarithm. Shannon's 1948 paper is, by any measure, one of the most consequential single documents in the history of applied mathematics. It established, from first principles, the theoretical foundations of communication, and in doing so, it answered questions that engineers had been wrestling with empirically for decades, without a clear framework. Before Shannon, the design of communication systems was largely empirical. Engineers knew from experience that adding more transmitter power made a communication link more reliable. They knew that using a wider frequency band allowed more information to be sent per second. They knew that noise corrupted signals and that corruption could be reduced by various engineering techniques. But they didn't have a precise answer to the fundamental question: is there a theoretical limit to how much information can be reliably transmitted through a given channel, no matter how cleverly you design the system? Shannon answered yes. He proved that every communication channel, every physical medium for transmitting information, whether it's a wire or a radio link or a fiber optic cable, has a maximum capacity, which he called the channel capacity. This capacity depends on two things: the bandwidth of the channel, the range of frequencies it can carry, and the signal-to-noise ratio, the ratio of the signal power to the noise power. And the relationship is logarithmic. The channel capacity in bits per second is proportional to the bandwidth times the logarithm base 2 of 1 plus the signal-to-noise ratio. This is the Shannon-Hartley theorem, and it is the fundamental limit of all communication engineering. The logarithm in that formula means that doubling the signal-to-noise ratio increases the channel capacity by only 1 bit per symbol, a fixed additive amount, regardless of what the signal-to-noise ratio already is. To double the channel capacity, you need to square the signal-to-noise ratio. To triple it, you need to raise it to the third power. The improvement in channel capacity from improving the signal quality is logarithmic, meaning that each equal multiplicative improvement in hardware yields only equal additive improvements in capacity. This is a law. You can't engineer your way around it. You can only approach the limit Shannon defined. Every engineer who has ever designed a modem, a cell phone tower, a Wi-Fi router, a satellite uplink, a Bluetooth connection, a deep space communication system, a fiber optic network, every one of them has been working within limits set by Shannon's logarithmic formula. The fact that you can stream video to your phone at all, that the pixels arrive correctly and in order despite the noise and interference of a crowded electromagnetic environment, is a consequence of error-correcting codes that Shannon showed must exist and that subsequent engineers built using his framework. The modern world of information is, at its mathematical foundation, a vast application of the logarithm. Shannon himself was a remarkable character. He was interested in everything. He juggled while riding a unicycle through the halls of Bell Labs. He built a machine that could solve the Rubik's Cube before the Rubik's Cube existed, a machine that solved a variety of mechanical puzzles. He built a one-person rocket-powered frisbee. He studied chess and poker and juggling as seriously as he studied mathematics, looking for the deep structural patterns in each. He was, by all accounts, a man for whom the world was an endless source of interesting problems, none more worthy than any other if they were interesting enough. He continued working at Bell Labs and later at MIT until the late 1960s, by which point the information theory he had created had become one of the foundations of electrical engineering and computer science. He spent his later life increasingly reclusive, eventually developing Alzheimer's disease and dying in 2001 in a nursing home in Medford, Massachusetts, without the Nobel Prize that many felt he deserved. The Nobel Prize in physics or in chemistry or economics, there is no Nobel Prize in mathematics or in engineering, and Shannon's work perhaps fell between categories. It is one of the more notable oversights in the history of the prize. There is another place where the natural logarithm appears that touches everyone's life in the modern world, even if most people never consciously encounter the mathematics. The concept of doubling time and its inverse, the half-life. When something grows exponentially, when each unit of time produces a fixed percentage increase in the quantity, there is a natural measure of the speed of that growth, the time it takes for the quantity to double. A savings account growing at 7% per year will double in roughly 10 years. A population growing at 1% per year will double in roughly 70 years. A bacterial culture doubling every 20 minutes will increase 1,000-fold in a little over 2 hours. The relationship between the growth rate and the doubling time is doubling time equals the natural logarithm of 2 divided by the growth rate. The natural logarithm of 2 is approximately 0.693. Divided by a growth rate expressed as a decimal, say 0.07 for 7%, gives approximately 9.9 years. This is the origin of the famous Rule of 72 used in finance. Divide 72 by the annual percentage growth rate to estimate the doubling time in years. The Rule of 72 is a convenient approximation of dividing 69.3 by the rate, which itself comes from 100 times the natural log of 2. The logarithm, compressed into a rule of thumb that millions of people use without knowing where it comes from. Thomas Malthus, the English economist, published his Essay on the Principle of Population in 1798, arguing that human populations tend to grow exponentially, doubling on some timescale, while food production grows linearly. The tension between exponential growth and linear resource production, he argued, inevitably leads to famine and collapse unless some external check, disease, war, poverty, limits population growth. Whether Malthus was right or wrong in his specific predictions is a complex historical and demographic question, but the mathematical observation that exponential growth eventually outstrips linear growth, no matter how large the linear growth rate, is a rigorous consequence of the mathematics of exponentials. The logarithm is what makes exponential growth so rapid. Each unit of time multiplies the quantity by a fixed factor, and multiplicative growth eventually beats additive growth by any finite amount. The logarithm captures the structure of this process, converting the exponential accumulation back into a linear reckoning of time. The recognition that populations, epidemics, rumors, financial bubbles, and many other real-world phenomena can grow exponentially, and the understanding of what that means, is one of the most practically important insights that mathematics has contributed to public life. At the start of an epidemic, when case counts are doubling every few days, the exponential growth is often underestimated because human intuition is not calibrated for exponential scaling. A disease that has infected 100 people and is doubling every 3 days will have infected over 100,000 people in 3 weeks. The logarithm of the case count tells you the true story. It grows linearly, 1 unit every doubling period. But people see the absolute case count, not the logarithm, and the absolute count looks small until very suddenly it doesn't. Epidemiologists routinely plot epidemic curves on logarithmic scales precisely because the logarithm converts exponential growth into a straight line, which is much easier to reason about. A straight line on a log scale means constant doubling time, constant exponential growth. A curve bending downward on a log scale means the growth rate is slowing. The epidemic may be coming under control. A curve bending upward means the growth rate is accelerating. Things are getting worse faster than they were. The shape of the curve on a logarithmic plot carries immediate, interpretable information about the trajectory of the epidemic. On a linear plot, exponential growth just produces a wall, a shape so rapidly increasing that everything before the last doubling is compressed into a barely visible baseline. The COVID-19 pandemic of 2020 brought this into sharp public consciousness. News graphics began showing epidemic curves on both linear and logarithmic scales, sometimes side by side, inviting viewers to compare. Commentators explained what a log scale meant. Public health officials learned, in real time, how to communicate about exponential growth to audiences whose instinct was to read numbers linearly. It was, in a sense, a public education in logarithms on a global scale. The logarithm was not just a mathematician's tool. It was a lens that determined whether you understood what was happening or not. Now, there is another place where logarithms appear, and this one is perhaps the most concrete and most visceral of all. It is the place where logarithms let us read the past. Radioactive decay is a process in which unstable atomic nuclei transform spontaneously into more stable configurations, emitting particles or radiation in the process. The rate of this decay is characteristic of each radioactive isotope, described by a quantity called the half-life, the time it takes for exactly half of a sample of the isotope to decay. Carbon-14, the radioactive isotope of carbon used in radiocarbon dating, has a half-life of about 5,730 years. Uranium-238, the most common isotope of uranium in nature, has a half-life of about 4.5 billion years, roughly the age of the solar system. The mathematics of radioactive decay is exponential. If you start with N0 atoms of a radioactive material, then after one half-life, you have N0 divided by 2. After 2 half-lives, you have N0 divided by 4. After 3 half-lives, N0 divided by 8. After T half-lives, you have N0 times 1/2 to the power of T. This is an exponential function, declining over time, never reaching 0, but continuously shrinking. Now, suppose you have a sample of material that contains some amount of a radioactive isotope, and you want to know how old it is, how long it has been since the radioactive material was last in equilibrium with its environment. You measure the current ratio of the radioactive isotope to its decay product. You know the initial ratio from physical chemistry, and you want to solve for T, the age. To solve for T in an exponential equation, you take the logarithm. You bring the exponent down, using the property that the log of a number raised to a power is the power times the log. The logarithm converts the exponential decay equation from an equation you can't solve for T into a simple linear equation that you can. The result tells you the age of the sample. This is what Willard Libby invented in the late 1940s, and for which he received the Nobel Prize in Chemistry in 1960, radiocarbon dating, the technique that uses the known half-life of carbon-14 to determine the age of organic materials: cloth from ancient Egypt, wood from medieval cathedrals, bones from prehistoric human sites, seeds buried in glacial ice, the Shroud of Turin, the Dead Sea Scrolls, the age of a mammoth tusk from Siberia, all determined by measuring a carbon ratio, knowing the half-life, and applying the logarithm to invert the exponential decay. The logarithm, in this application, is literally a time machine. It takes a measurement made in the present and converts it into a date from the past. Without the logarithm, the calculation cannot be done. With it, the calculation is almost trivial. A few multiplications, a table lookup, or today, a few keystrokes, and the answer is a number of years, a window into history that no written record could provide. And here is something that might shift how you think about logarithms entirely. If you ask a group of adults who have not studied mathematics carefully to place numbers on a blank number line, to mark where they think 10 belongs, and 100, and 1,000, and 10,000, They will generally do it linearly. 10 is near the left. 100 is further. 1,000 is much further. 10,000 is near the right edge. Equal physical distances represent equal numerical differences. That is the standard number line. That is how we are taught to think. But if you ask young children, children who haven't yet had significant mathematical education, to do the same task, something different happens. They place numbers logarithmically. 10,000 doesn't go near the right end of the line. It goes in the middle, because it's between 1 and a billion in a logarithmic sense. Because the ratio 1 to 10,000 is the same as the ratio 10,000 to 100 million, and ratios are what the untrained mind naturally compares. This finding, from research by Stanislas Dehaene and his colleagues, published in the early 2000s, studying both children in Western schools and adults from an Amazonian indigenous group called the Munduruku, who had no formal mathematical education, suggests something profound about human number sense. The linear number line is not our default. It is something we are taught, something that requires cultivation and training, something that replaces a more natural, logarithmic intuition about numbers. The untrained human brain, it appears, thinks logarithmically about magnitude. 1,000,000 and a billion feel closer together than 1 and 10, even though arithmetically, the gap between 1,000,000 and a billion is much larger. This is not stupidity or innumeracy. It is a reasonable way to represent a world in which the important distinctions are often between orders of magnitude, not absolute differences. A predator 50 meters away is twice as dangerous as one 100 meters away, but both are far more dangerous than one a kilometer away. The ratio matters more than the difference. This means that logarithms are not an alien imposition on human intuition. They are, in some deep sense, a formalization of how we naturally perceive magnitude. When you struggled with logarithms in school, it may not have been because logarithms are counterintuitive. It may have been because the linear number line, the thing you had spent years learning, is itself counterintuitive, a trained replacement for the logarithmic sense you were born with. Logarithms aren't the hard part. The linear scale is the hard part. Logarithms are where you started. Think about that. You arrived in the world already equipped with a logarithmic number sense. The universe compresses its magnitudes into logarithms for you, presenting the incomprehensibly wide span of physical reality in a form your brain can hold. Your ears do it with sound. Your eyes do it with light. Your intuitive sense of quantity does it with numbers. You have always been, in this sense, a logarithmic creature. The mathematics that Napier worked out over 20 years, and that Briggs refined into the tables that changed the world, and that Shannon applied to the theory of information, and that every engineer who ever used a slide rule embodied in their hands, that mathematics is, in some sense, an externalization of something your nervous system already does, a formalization of a capacity you were born with, a language for something you already knew. The Munduruku study by Dehaene and colleagues was published in the journal Science in 2008, and it caused significant discussion among psychologists and educators. The Munduruku are a people of the Amazon rainforest in Brazil who have a highly limited number vocabulary, words for numbers only up to about 5, with larger quantities described approximately as many. Their language does not have the elaborate numerical structure of Western languages, and their culture does not involve counting, measuring, or formal arithmetic in the ways that shape the numerical cognition of people who grow up with formal education. Yet when Munduruku adults were given a number line task, asked to indicate where numbers fell on a line from 1 to 1,000, or 1 to 10, they systematically placed numbers logarithmically. 100 did not go at 1/10 of the distance from 1 to 1,000. It went roughly halfway, because it's the geometric mean, the square root, of 1 times 1,000, and the logarithm of 100 is halfway between the logarithm of 1 and the logarithm of 1,000. Similarly, educated Western adults also placed numbers logarithmically when the numbers were large and unfamiliar. When asked where 1 billion fell between 1 and 1 trillion, they tended toward the middle, not toward the 1,000th mark where it linearly belongs. The conclusion that Dehane drew was that approximate number sense, the sense of relative magnitude that all humans share, is logarithmically organized. The mental number line is a logarithmic number line. Formal mathematical education in literate, numerate cultures gradually trains people to think linearly for smaller numbers, but the logarithmic intuition remains for large numbers, and it is the baseline for people without formal training. This has significant implications for how we teach mathematics. If children's intuitive number sense is logarithmic, then teaching them the linear number line requires an active overwriting of an existing structure. It requires effort and reinforcement, and it may explain why many children and adults who are otherwise intelligent and capable find formal arithmetic and large numbers counterintuitive. Not because the mathematics is alien to their minds, but because the linear number system is what's alien, and the logarithmic sense is the natural one being suppressed. More recently, researchers have found that even in Western children, the transition from logarithmic to linear number placement for smaller numbers happens gradually over the elementary school years, with different number ranges becoming linear at different ages. A typical 6-year-old places numbers from 1 to 100 on a roughly logarithmic scale. By age 8, numbers up to 10 are placed linearly, but the larger part of the scale remains logarithmic. By about 10, the whole scale from 1 to 100 is linearized. This progression suggests that the linear number line is not discovered but constructed, built through education and practice on top of a logarithmic substrate. And this should change how we think about the question of why logarithms feel confusing. The usual explanation is that logarithms are advanced mathematics, far removed from everyday intuition, requiring years of training to really grasp. But the evidence suggests something different. Logarithms are primitive mathematics, the mathematics of the untrained mind, the mathematics that evolution built into our number sense, because it was useful for navigating a world of magnitude ratios. The formal logarithm that Napier invented and Briggs refined and Shannon applied was a conscious construction of something that human perception had always been doing unconsciously. The difficulty students have with logarithms may not be a difficulty with a foreign idea, but the difficulty of recognizing in abstract symbols something their own minds have been doing all along. So here we are, a concept that started as a desperate practical need, a need to make multiplication manageable for astronomers drowning in arithmetic and navigators risking their lives on the accuracy of their calculations, has turned out to be one of the most fundamental structures in mathematics and in nature. Logarithms are not just a calculation shortcut, they are the language of exponential processes. They are the mathematics of perception. They are the key that unlocks the measurement of information, of time, of sound, of acidity, of magnitude. They are built into your ears, into your visual system, into your intuitive number sense. They are the slide rule in Neil Armstrong's pocket and the equation behind every compression algorithm that keeps the internet functional, and the carbon-14 ratio that tells us how old the oldest human remains are. And there's a beauty in the way all of this connects. Napier's insight, that multiplication in the world of numbers corresponds to addition in the world of their logarithms, turns out to be a special case of a much deeper truth, that processes which multiply tend to produce logarithmic structure everywhere they touch, populations that grow by multiplication, sounds that pile up by multiplication of pressure waves, neurons that sum up logarithmically compressed inputs, uncertainty that multiplies when you combine independent sources of randomness. In a world full of multiplicative processes, the logarithm is the natural coordinate system. It converts multiplication into addition, exponential curves into straight lines, wide-ranging scales into manageable intervals. Your brain understood this before you had words for it. Napier gave it words, and a table, in 1614. Briggs simplified those words into base 10. Oughtred turned them into a physical instrument. Euler found the constant E at the heart of it all. Fechner saw it in perception. Sorensen used it to describe acidity. Richter used it to measure the Earth's trembling. Shannon used it to measure the surprise in a message. And all of them were, in different ways, making precise a structure that the world had always possessed. And there's one more way to see the unity of all of this, which is to recognize that all of these applications, the decibel, the pH, the Richter scale, the magnitude of stars, the bit, the half-life, the algorithm's log n complexity, the musical semitone, are all instances of the same basic insight that Napier had in 1590 and Briggs refined in 1624. They are all cases where someone looked at a quantity that varied over an enormous, unwieldy range, or a process that grows and decays multiplicatively, and said, the natural way to measure this is not the linear way. The natural measure is the exponent, the logarithm. Every time a scale compresses the wild range of reality into something a human can grasp, navigate, and communicate about, every time a factor of a trillion range becomes a 12-unit scale, or a factor of 10 billion range becomes a 14-unit scale, or the impossibly wide range of information content becomes a bit count, the logarithm is doing that compression. It is the universal translator between the multiplicative arithmetic of nature and the additive arithmetic of human thought. And the fact that your perceptual system already does this, that your ears and eyes and sense of number already work this way, is not a coincidence. It is the answer to a question that evolution asked and answered long before Napier. How do you build a nervous system that can navigate a world in which the important quantities, light intensities, sound pressures, distances, population sizes, span many orders of magnitude? The answer is, you build logarithmic sensors. Sensors that respond not to the absolute magnitude of a stimulus, but to the ratio of the current stimulus to a baseline. Sensors that compress wide-ranging physical realities into narrow, manageable perceptual signals. Sensors that compute, in their very structure, the logarithm. Napier formalized something that biology had already discovered. Shannon quantified something that every nervous system already does. The mathematics of logarithms is, at some level, the mathematics of intelligent perception itself. There is one more thing worth saying about logarithms before we let the ideas settle. The way they changed, not just what was computable, but who could compute it. Before logarithms, serious mathematical calculation was the province of specialists. Astronomers, mathematicians, navigators, trained in trigonometry. To do the calculations required not just the knowledge of the methods, but years of practice at the physical act of long multiplication, building up speed and accuracy, and the psychological stamina to sustain many hours of tedious computation without losing focus. It was a skill, like playing an instrument, that required cultivation and maintenance. Most people did not have it and could not acquire it easily. After logarithms, and after the slide rule, serious calculation became accessible to a much wider range of people. An engineer who was not a professional mathematician could nonetheless perform complex structural calculations using a slide rule in minutes. A chemist could calculate reaction stoichiometries without a lengthy arithmetic education. A navigator could perform celestial calculations from tables and rules of thumb built on logarithmic shortcuts. The democratization of calculation, the expansion of who could do quantitative work, was one of the quiet social consequences of Napier's invention. This democratization continued with each subsequent tool: the mechanical calculator in the 19th century, the electronic calculator in the 20th, the spreadsheet and the computer in our own era. Each tool lowered the barrier to quantitative work further, but the first and in some ways the most consequential step was the logarithm, which took a process requiring specialized training and years of practice and reduced it to a table lookup and an addition. Napier did not just help astronomers and navigators, he changed who could participate in the quantitative description of the world. And there is something in that worth holding on to as you drift toward sleep. Mathematics is often presented as a gatekeeping mechanism, as a barrier that separates those who can handle it from those who cannot. But the history of mathematical tools is largely a history of barrier lowering, of finding ways to make the complex simple, the tedious fast, the specialized general. Each generation builds tools that make it easier for the next generation to stand on their shoulders. Logarithms are one of those tools, and the fact that they also happen to be built into your nervous system, that you were already, in some sense, using them before you ever heard the word, makes them not a foreign imposition of mathematics on an innately enumerate mind, but a recognition of something that was always there. Right now, as you settle toward sleep, your auditory cortex is receiving signals from your cochlea that have already been logarithmically compressed. The range of sounds in a quiet room, the faint hum of whatever device you're using to hear this, perhaps, the distant sounds of the world outside, has been converted by your inner ear from a ratio of intensities into a manageable spread of neural firing rates. Your visual cortex, if your eyes are open or even if they're not, is processing light signals that have been logarithmically compressed by the photoreceptors in your retina. The neurons in your brain, firing and connecting and building the thoughts that will dissolve into sleep, are doing what neurons do: summing, compressing, transforming. There is, in a sense, logarithmic processing happening in the hardware of your body at this very moment, the way there always is, the way it always has been. You have always been computing logarithms. And now you know a little more about what that means, and how a Scottish nobleman with 20 years and a burning need to help the navigators, and a London professor who took a long journey north to sit in silence with a fellow mathematician, and a Swiss pastor who discovered E in a compound interest formula, and a reclusive genius at Bell Labs who figured out how to measure surprise, how all of them, across 4 centuries, were slowly giving names and structure to something the universe had always been doing. That's a good thing to carry into sleep. The knowledge that the world is stranger and more wonderful than it appears, and that understanding it, even a little, is one of the finest things a human mind can do. So let that settle, let the ideas drift, and let the logarithmic processes in your neurons do what they do, quietly, reliably, carrying you gently into sleep. Rest well.